So everybody, welcome back. I'm pleased to have Marco Morazán with us. We all know that Racket is used a lot in teaching, right? I mean, sure, we all like to hack a ton. We waste our weekends hacking Racket. But Racket is also used for teaching, and it was a delight to get a couple of talks about Racket as a tool for teaching. Marco will be the first one, then we'll have another one also about using Racket for teaching, and we'll have another coffee break, okay? So, Marco, take it away.
Thank you. Okay, so feel free to interrupt whenever you like. If I don't get to the end of my talk, I'm perfectly fine with that, because I'd rather have a good discussion than to rush through all the slides. Right, so feel free to interrupt. Okay, so, right, when we teach beginners, one of the things we have to decide is what is important for beginners to learn. And I'm sure all of us here can make up our own little list of what's important, and I would bet that the intersection of these lists are not empty. So let's not quibble about the differences. Let's see what we can all agree on. Right, so for example, you need to teach them how to design solutions, how to express these solutions using some syntax. And you have to teach them about abstraction, modularity, all these key words, right? Iterative, refinement, documentation, testing, essential, right? Complexity, efficiency, empirical experimentation, which I think is neglected in undergraduate education. It should be fun too, right? We shouldn't be boring our students. And whatever they learn should be relevant, right? In other words, we shouldn't be teaching them stuff that they're not going to see in the next 50 years in any practical sense. Okay, so the question is, can all of this be done with beginners? And is it done with beginners? And so to answer that, right, I want to give you this function here, right? So everybody knows what that function does, correct? Come on, it says quicksort on top. So, and we all know quicksort, right? So, and I looked at this function and I was like, holy cow, right? And I don't mean to pick on this one book or this one website, but it does say it's a beginner's book there, right? So I was like, oh Lord, how can we be teaching beginners that? Right, so there is no abstraction here, there's no modularity, there's no documentation. Right, so for example, there's these two while loops there. What do those things do? Right, of course, they're searching for the numbers less than or equal to the pivot and greater than to the pivot from the right and from the left, correct? So that's a screaming auxiliary function. Why should we be doing this here? And then you have this code there that is just simply repeated, right? And we all know what that is. That's just the swap operation. And again, that's what? Screaming for abstraction, write an auxiliary function for it. Okay, so we can do that. But then again, we still have what is this? Right, another while loop in there. And of course, I've never met a while loop that doesn't try to solve a problem. Right, so if you're going to solve a different problem, write an auxiliary function for it. Right, and that's the loop that partitions the vector, right? Okay, so if we do all that, this is what we get. And right now this reads like quicksort. Much easier to realize what it does. Yes, power to the people, Sharon. Okay. Okay, so how do we get beginners there, right? How do we get them to this point so that they can hand in well-designed code like that? Okay, by the way, I do take care of this problem too. So if I had a student that ever handed in that right, they would get an earful from me, right? Right. So, right. No, you never use a conditional to compute a Boolean function. Period. There's an easy rule to follow. Okay. So the best approach I've ever seen to getting students there is how to design programs, of course. Teach them about design, about problem solving, right? About following the data. And I always sold this book as the best textbook ever written in computer science. Used it for years, but it wasn't perfect for our situation at Seton Hall. Number one reason, it's too heavy. There's too much material to do it effectively in one semester. So the students were struggling towards the last two parts of the textbook. They struggled, right? Generative recursion and cumulative recursion. Just not enough time for them to learn that well. It has another problem, in my opinion. It's a hard transition from the prescriptive design recipes that use structural recursion to the non-prescriptive design recipes like for generative recursion. It does sidestep the needs of non-functional programming professors, right? And this is one of the big reasons that people always complain. They say, look, I want you to teach them about objects and while loops and mutation and stuff like this. Completely the wrong thing to do with beginners, but I was a communication major as an undergraduate, and I learned the lesson, never ignore any of your audiences. So I'm going to try to address that. It doesn't have a large project where they can see the power of iterative refinement, right? This idea that not every function is 6 or 7 lines of code, right? You could have bigger programs. And then, of course, there's this hard transition, right, to the non-prescriptive, but with no intermediate material that could make the transition easier.
What do you mean by non-prescriptive?
Generative recursion, for example. So when you do structural recursion, you know exactly where the recursive calls are going to go. But when you do generative recursion, you don't know this, right? You need to analyze and have more insights into the problem. And so the students are dealing with something that's not prescriptive, and they're dealing with this idea that they have to really analyze the problem to figure out where the recursive calls come from.
I think the book even says aha or eureka.
Yeah.
For this.
Yeah, but that's difficult to get to work, right? I can't get aha to work all the time. Right, so my solution was to break up the material into 2 semesters, and I'm happy to say 2 new books are in print using the student languages, so feel free to take a look at them. So in animated problem solving, we do all the basics, expressions and functions and structures. We do structural recursion, functional abstraction, and then we end with something that is relevant. It's called distributed programming. And then in the second semester, we start with distributed programming, where we left off, and we introduce them to randomness, to generative recursion, to accumulative recursion, and to mutation. And so that's how the material is divided for us over 2 semesters. And there's reasons for this type of division. So the first is that distributed programming is less prescriptive, and I'll show you a little bit about that. So when they write their distributed programs, every function that they write is using structural recursion, which they're familiar with, but they're fulfilling the steps of the design recipe that is not prescriptive. Yes?
With the stuff with mutation, do you actually use like the advanced student language, or do you just use bracket?
Advanced student language.
Okay.
And a lot of other stuff. I'll try to talk about it. Let's see how much time I have. Okay, and I try to also introduce them to advanced concepts like property-based testing, which is necessary when we do randomness, right? Because you can't predict what the answer is. And so the motivating example through the first book is something like called Aliens Attack, which is like Space Invaders. And in the second book is the end puzzle problem. Everybody familiar with the end puzzle problem? No, I'll show you. Okay. Okay, so let's be beginners, right? So put your beginning hat on, right? And right, this is the goal, right? You want to create a game that looks like that, right? And the question is, how do you do this, right? So they have to learn a lot of stuff, right? They have to learn about expressions. They have to learn about conditionals. They have to learn about structural recursion, about structures, right? And then a whole bunch of magic happens in that process. So for example, consider moving a list of aliens. So what do you do? What does how to design programs tell you how to do? Well, define what a list of aliens is, right? Show me that you know what that is. And define some sample values that are lists of aliens. And then the rest of the design recipe is, for now, the next step, I should say, is the template. And for us, the template, right, includes the usual stuff, right? The signature and the purpose, and template for the function definition, but the template also includes sample expressions, tests, and two types of tests. So the sample expressions is where I ask the students, show me how to compute a value for each subtype of the data. Right, so for a list of aliens, here's the answer if it's empty. Here's the answer if it's a non-empty list of aliens. Here's how we compute the answer. And then the test using sample computations test the sample values that were computed. And then the other tests are more how to design programs where you actually use values that were not predefined. Okay, so let's actually write this. So here are my sample expressions. And you can see, right, if it's the empty list, you just return it. There's nothing there to do. But when the list is not empty, let's say we are moving to the left, so we'll move the first alien to the left and then move the rest of the aliens, and we move the first alien to the right and then move the rest of the aliens to the right. And so now students can what? Identify the differences between those two expressions, and those are the parameters of the function. And then they can use abstraction over expressions to actually come up with the code in the body of the function. Right, so there's the header, right? Two differences, so two parameters, and they write their tests, right? So clearly, right, the function should compute the values of the sample expressions, and it should also work for other stuff that wasn't predefined. And then in the body, right, since there's variety in the data, we need a conditional. So if it's empty, well, now they can look, okay, the answer is always empty, so they can write that in. And then they abstract over these that look very similar, right? And they have this function. Now, the reason I do it like this is because I once was trying to help high schools in inner city Newark to teach programming. And when I told them they had to write a function, they looked at me and said, what is a function? Are you crazy? That's always given to us. And I began to realize that they didn't understand where functions came from. So by teaching them how to abstract over expressions, they begin to understand where functions come from. Okay. Now, of course, you do the same thing for a list of shots. And what happens is that you end up with two things that look incredibly similar. And this is where, right, you take advantage and you say, well, let's do functional abstraction. And you're going to teach them how to refactor that code so that there's only one recursive function and the other two are defined in terms of that function. There's a little problem in this example, right? Because the structure of the function is not the same. Right here, you're applying a function to one argument, and here you're applying it to two arguments. So you need to do some code refactoring, right? They see the need for this. And so you say, okay, well, how about if we just create a function to move an alien in the given direction? So, okay, well, they've studied lambdas, they know local. They say, okay, let's put this together, and you get this. Right, so there's an alien function to create functions that move an alien in a given direction. And now you see that the structure of the two functions are the same, and you can do functional abstraction, and you know where this is going, right? So this is going to lead us to map. Yes?
I would argue that that is not well what
I can't,
I would argue that for most students, the inclination would be to add dummy parameters so everything evens out.
I've never had a student do that, but it would be an argument I would entertain.
Small universities, then you have more players.
Somehow I question that conclusion, Shiram, but right?
I mean, the way I've always seen it is that people would rather put a lambda or a local in there. I have seen, we had a question kind of like this one where you needed to make a function that returned a lambda on like one of the midterms at IU last year, and including the honor students, 2 people got it. And these people understood like local, they understood lambda, but they didn't know that you would just return a lambda from a function. Like they assumed that it was a thing that was passed to other functions.
No, we make it a point that you evaluate a lambda function, the result is a function.
Okay.
Right?
Yeah.
Okay, but look, something wonderful has happened now. because now they've discovered, right, what is a curried function, but that's using functional programming jargon. We don't have to use functional programming jargon. We can say, hey, look, you've discovered classes and objects. So this is make alien mover is a class that returns objects that knows how to move an alien in a direction. And then we can have fun with this and satisfy that other audience and say, look, let's define what geometric shapes are. So we have a data definition for geometric shapes, and we talk to them about defining the behavior that's expected from a geometric shape. Okay, so we can say, look, I want to know if it's a square, a rectangle, a circle. I want to know the area of the shape, and I want to know if this shape is bigger than some given shape. And so they learn about interfaces, right? They write them down as comments, and then based on that, they can write a template for a class. And this brings the material to a domain that's familiar to them, or at least they feel familiar with it, right? So to make a geometric shape, well, you're going to need a function to determine if one is bigger than the other, and then you're going to need a function to process messages, and depending on which message you get as input, that's the type of value that you return. And then the name of the game, once you get them to this point, is the same as before. Whatever problem you want to solve, specialize the template. So here we go, right? Here's the specialization when you want to make a square. The template.
That what you were matching was, is this square a name of a function? What are you matching against? It's a function. I thought that's a function of value.
Good. There's typos here. These are all symbols.
Okay.
Sorry. Yeah, those are typos. Okay. As you can see, they're corrected in the next slide. Okay, so we can teach them a little bit about objects and classes and interfaces. And then after that, we make the transition to the first non-prescriptive design recipe, which is distributed programming. And there's the goal, right? Multiple players trying to defend against multiple aliens. And they have a design recipe that looks like this, right? And if you look at the steps here, right, divide the problem into components. That's not prescriptive, right? So they need to know what is expected from the server, what is expected from each player. You draft data definitions, familiar territory, new stuff, design a communication protocol. Again, a non-prescriptive step, but they can do it. And then they design marshalling and unmarshalling functions to communicate data. And that is using all the design recipes that they already know. So there's no struggle there. And then they implement the components, again, using all the design recipes that they have already studied. So we're not asking them to also figure out where the recursive calls are. Okay, so now in the second semester, right, the motivating game is this, the end puzzle problem. So for those of you who didn't know, right, you just have to put the tiles in order. And the interesting thing here is the help me button, because the player can ask for help and make a useful move for the player. So I asked the students, right, what do you want to do? You want to find a sequence of moves that takes you from the given board to the winning board. How do you do that? And you have to spend some time, you have to be willing to burn some class time so to let them reason this out. And eventually they say, okay, well, I want to make a move from the given board, B, and from that new board, I want to find a sequence of moves to the winning board. And they say, oh, yeah, it's recursive, but it's no longer structural recursion. Right? This is generative recursion. So I let them discover on their own a generative recursive solution to a problem. And now, they have to learn, that motivates learning about generative recursion. And the interesting question for us here today is, how do you make the move? Right? How do you make that move? So immediately, despite teaching them about randomness, the students say, pick randomly. I don't know how to pick a successor, pick it randomly. Okay. Right, so, yep, we get the neighbors of the blank, we randomly pick one, that's the move that we have to make. That's the move that we make. And they run it. At best, it's slow, but more frequently than not, it runs out of memory, right? It's not an effective solution. So now they have to study more stuff, right? And then the next step is say, well, look, let's not pick something randomly, right? This doesn't make sense. We're not generating passwords here, right? We don't want to pick something randomly. Excuse me. So you say, okay, so they're going to learn about depth first search. Right? I motivate depth first search this way. And then you say, well, look, what I'm going to do is I'm going to use a heuristic. So I'm introducing them to a small step of AI, if you like. And say, here's a rule, right, to pick the best successor. And so they say, okay, we're going to pick the best successor and find a solution from there. Wow, okay, so look, we have accumulators now, right? I'm sorry, yeah, we will have accumulators, right? But there's a problem with this because it can end up in an infinite recursion. So sometimes it works and sometimes it doesn't work.
Where did best child come from?
Excuse me?
Where did best child come from?
I'm sorry.
Where does best child come from? Like,
Oh, that's the function that uses the heuristic to pick the best one. So we use the Manhattan distance, but I don't want to get into the details of what heuristic we're using. There is a heuristic.
but that heuristic is not doing a search.
So?
Is that heuristic is not doing a search in itself, right?
No, it's just evaluating, right? Evaluating the successors of the given board. Okay. So we have to explain why this goes into an infinite recursion. Jay, where are you? We see your trees there, right? We definitely teach them about trees, and they can see why, right? When you have repeated boards, it'll just go into an infinite recursion. Easy to understand, but again, you have to be willing to burn class time for them to get there. Okay, so then we say, okay, well, let's not ignore all the other non-best successors. Let's explore them all. Right? And this is breadth first search. So they get to learn about breadth first search. And when they implement it, right, you see, well, now we search the path with the rest of the paths. Okay, that's structural recursion. And there's an accumulator that remembers all the paths that have been generated so far. So they run it. It's slow. It's slow. And I have to tell you, there's nothing worse than a slow video game, right? I mean, that is just the pits, right? So we still need to do better. So in our next refinement, again, following this iterative refinement process, we introduce them to A star. And the idea is, well, let's combine depth first search with breadth first search. Two topics that they've just seen. Right, so we're slowly building their knowledge base. And of course, then here what they do is that they create new sequences only with the best, they create new sequences from the best sequence that has been accumulated so far, and that's what's used to make the recursive call. So you're not exploring all the paths at once, you're being selective about which new paths you create.
I'm going to argue that the code on the screen has a little bit of the flavor of the bad Pixar show definition.
Okay, give it to me.
These two ideas I've already seen, which is breadth first and depth first. But I don't see breadth first and depth first being very important. I see like a whole slide in our book.
Yeah.
That's the next slide.
So, no, I don't have a slide for that because I only had 20 minutes. But right, there's no way you can just hit them with this code. Right, you need to have them map it out, right, to see how it works. Right? Okay, so if they do that, right, and then they discover, right, that really works, and then you could do cool stuff like the empiricism that I was talking about. Right, so they can time, right, these works, and more than once, right, because we need to tell them about averages and standard deviation and relative difference. But, you know, when they look at the data like that, right, it's inspiring to them, right? So they can see now why, for example, depth first search, when it works, can be extremely slow. Yes?
What are the 1, 2, 3, 4?
5 experiments. We ran the experiment 5 times.
No, it was column, sorry, rows.
Yeah, so the first DFA, we ran it 5 times. Then there was another problem using DFA, we ran it 5 times.
So these are 1, 2, 3, and 4 in the column.
Oh, wow, yes. 4 different problems that got executed 5 different times. Yeah, and they got executed for each one of the algorithms. Right, so we go back to Jay's trees, right? If the computer has to calculate a solution that's 26,000 plus moves, you understand, right? And you're going deep into the tree, and this is why it's so slow. And then they can also see that A star is the king because it's lightning fast. They also appreciate, right, that breadth first search is finding what? A really efficient solution. It doesn't go deep into the tree. So why is it slow? Well, now they think about it. If the tree is wide, right, that could slow down the process. And therefore, A star could be faster. Okay. And then, right, I could say, let's be advanced students, but I have a feeling I don't have time for that. Really? It would be fun to talk about that because here we get to tie in logic, right, with programming, right, in sequencing mutations. So students walk away saying, oh, I understand why logic is useful for computer science. Okay. So, can this be done with beginners? My answer is it can be done, and it can be done effectively, right? Because they have fun doing it as they develop different versions of a video game. Okay. So before I stop, I have a plug. Stephen, where's Stephen? Is Stephen here? Stephen is running TFP in Boston this January, so please join us. Come give us a talk. Fully baked, half baked, only an initial idea. Or we are interested in all types of coherent talks. Okay, so and Stephen can give you a lot more details. So on that note, any questions?
Thank you.
So I don't really have a sense of a timeline here. You keep using words like beginner, and I don't know what those mean. So go back to like 2 slides back. How long does all this take?
So these are things that are emphasized throughout, right, from the beginning.
But we're trying to like semester terms. Like how long? Literally how long?
So in the first semester, I outlined it, I believe. We go from basics, expressions, all
So
the.
let's book the first semester, the right book the second semester.
Yes.
So this is, we're looking at a year long.
Yes, this is a year-long sequence. Yep. Yeah.
Another question.
Go for
How do
it.
you know this works?
What's that?
How do you know this works?
I know it works because I have 2 answers for that. I haven't measured it, but the quality of my students upstream when they get to the upper level courses is better than what I was getting before. Right, so that's one measure, informal measurement that I have. And the other one is that I could see the reaction of my students in class. Right? They feel good when.
When you say upstream, do you mean other professors' reviews?
Well, I get them in higher level courses, right? In upper level courses.
Yes, but are you the one evaluating them in upper level courses?
In the ones that I teach.
Okay.
Yeah.
Have other professors who have had your students follow this?
Yeah.
Go
What
on.
do they say?
What do they say?
Yeah, I don't know yet. The one professor who had some experience retired. Well, Shiram knows about this. He said, Marco, apparently what you're doing works.
Okay.
But I still think it's the wrong thing to do. So you explain that to me, however, if you can, right? Christian?
I was just wondering, since something like a video game approach could be seen as more like polarizing and like attractive to certain audiences, what are your generations like?
Yeah, so it turns out that, again, anecdotal experience, that this is a great way to retain female students in computer science. They love the fact that they can personalize their games, and that their solution is not the same as the solution of somebody else who is working on the same game. So it actually has a positive net effect.
What were the primary areas in this list that people were having struggles with when they moved through the program, like that you addressed with this new curriculum?
Well, functional abstraction is always a bit hard for them to absorb, but in the whole year semester, definitely the hardest part is mutation, the part that I didn't talk about, right? So we teach them about while loops and loops invariants, and right. For a beginning student or a second semester student to actually develop a loop invariant, that takes quite a bit of work.
And of these different areas, which do you expect to gain more significance in the course, or which areas you think might have less significance as you change the program? So,
for example, if I were to fall behind, I would suppress the stuff on classes and objects because they'll get that in some other course upstream. For example.
When and how do you introduce mutation?
When and how?
Do you introduce mutation?
So, that was my next year talk, but I'll tell you. What we do is we teach them about a cumulative recursion, and we show them a trace, right? We trace it, and you can see that there's only a single value that's needed for each one of the accumulators in the program. And you say, well, look, instead of making all these recursive calls, let's just change the value of these variables as the program progresses. And then that's how we introduce them to mutation.
Final question?
Okay, so a bit off topic, but one thing that I absolutely dislike, and dislike of, is like in HTTP as well, is the naming of variables are really unreadable. Like, LOS and stuff like that.
I admit that I struggle with that too.
Yeah, so,
I admit it. Especially when the number of tests grows, it's really hard to come up with good variable names. But you know what? I think it's more important to write the tests despite having terrible variable names.
There are 26 letters on the keyboard.
That's right, Jay. That's true. There are. But not all sequences of letters are significant.
All right, thanks, Marco.
Okay.